So in the previous class, we have seen that plane polarized light can be of horizontal polarization, which is denoted as P polarization, and the vertical polarization, which lies on the vertical plane, is called S polarization. Let us know a little bit more about randomly. Randomly polarized light is, of course, the one where the electric field, of course, the magnetic field as well, oscillates in all possible directions. On the plane, which of course is orthogonal to the direction of propagation. So the electric field shown here is oscillating in all directions random. So light with random polarization will essentially have an electric field oscillating in all the planes lying between 0 and 2 pi angles. If you take this as 0 degree, then this is rotating from 0 to 2 pi. So for a random polarization, electric field will oscillate in all the planes lying between 0 and 2 pi angle. Now, electric field being a vector, the randomly occurring fields can be resolved into two components, one lying on the horizontal plane, other on the vertical plane. So basically what we are trying to do, we are trying to resolve the random polarization into two polarizations, vertical and horizontal. Because you see, this one, for convenience, let us draw this plane as this, on which oscillation of the electric field is occurring. And the direction of propagation of light is perpendicular to the plane of this paper, either in or out. So now let us consider. So this is, say, vertical axis, this is horizontal. And let us consider, just for convenience, two electric fields. So this is E1, which is making an angle θ1 with the horizontal axis. Another field E2, which is making an angle θ2. Now if we resolve E1 along the X and Y, then it becomes, along X it becomes E1 cos θ1, and the component of E2 along X direction is E2 cos θ2. This is along the X direction. And E1 sin θ1 plus E2 sin θ2 is along Y direction. Therefore, we can say that this two electric field is equivalent to this much field in X direction and this in the Y direction. These two together will create an effect which is equivalent to this. In other words, we can say when it take off all the electric fields which are oscillating randomly all around for the entire 0 to 2 pi angle. Therefore, equivalently, we can say that unpolarized light comprises of horizontal and vertical polarization in equal amount because it is random. So if you add up the component in this direction and in this direction, they will be equal. So now in the same, applying the same concept, we can say that a horizontal polarized light has the entire component along the horizontal direction and zero component along the vertical direction. And a vertically polarized light has the entire field component along the vertical direction, zero in horizontal. A randomly polarized light has both vertical and horizontal components, but of equal. I hope you have understood the concept of randomly polarized light and how it differs from plane polarized light, which can be both vertical as well as horizontal. Now let us try to understand what is meant by Brewster. It is a very intriguing and interesting concept which has very important effect on impact on the field of optics in general. In 1811, Scottish physicist David Brewster made a profound discovery, which is now popular as the Brewster or polarization angle. Let me mention here, the Brewster angle concept can be exploited to manufacture polarized light from a laser. We will see it during the course of this, as we move forward in this course, wherein practically no light is lost into the unwanted polarization. Brewster found that the reflection of unpolarized light from an interface of two optically transparent media not only depends on the angle of incidence, but also on the state of polarization of light. So for instance, let me tell you, you know that on an interface separating two optically transparent media, say, let us assume that this is media of refractive index mu1 and this is a media of refractive index mu2. When light shines on such a surface, you know that a part of light is reflected and the rest is of course refracted into the second medium. Whether it will bend towards the normal or away from the normal would depend on whether it is a denser medium or a rarer medium with respect to the incident medium. We also know that the reflection of light depends on the angle of incidence. If the angle of incidence changes, the reflectivity also changes. The reflection of light changes with angle of reflection. For instance, you can recall that when light shines normally on a surface, if it is the air to glass interface, then according to Fresnel's law of reflection, 4% of the light is reflected back from the surface under normal incidence. If the angle of incidence increases, then the reflection percentage increases. But Brewster found that this reflection not only depends on the angle of incidence, it also depends on the state of polarization, whether this light is P polarized or S polarized. It depends on the state of polarization. He also found that generally the S polarization, that is perpendicular polarization, S polarization undergoes higher reflection and P polarization undergoes higher refraction. And as a matter of fact, at a particular angle of incidence called the Brewster angle, reflected light comprises entirely of the S. At a particular angle of incidence, the reflected light cannot be P-polarized light. So basically then what we see is that the reflected light is comprises mostly of S polarization. Therefore now we can say that the glare in the vision that we saw in that picture, the reflected light, that is the glare, is thus primarily linked to this polarization, S polarization, which is mostly reflected. So the glare actually contains S polarization. A polarized glass blocks this polarization to make the viewing both pleasant and soothing. Professional photographers often make use of the same principle to acquire a clear and sharp image of an object beneath a reflective surface such as water or glass, as we had already seen in the picture that I shown at the beginning of this lecture. Now, how the polarizer blocks light of a specific polarization, as in that case, this polarization. The mechanism of removal of waves of a particular polarization in the case of a transverse wave can be readily understood by considering, for example, the case of such a wave moving through a rope, a transverse wave moving through a rope. We conduct two experiments. In the first experiment, we set a rope wave, transverse wave, on one side of the rope, as you can see here, on a vertical plane. So this wave has been impressed on a vertical plane. And now what we do, let the other end of the rope pass through a horizontal slit. Now you can appreciate that this horizontal slit will block these vertical disturbances. It will not allow it to move. And so the wave would simply die. In the second experiment, you rotate this horizontal slit and make it vertical. Now it is clear the wave will now pass through this unhindered. The vertical wave now continues its motion without any hindrance to the vertical slit. Likewise, an oscillation in the rope when impressed on a horizontal plane. Now this oscillation is impressed on a vertical. If you impress this on a horizontal, this oscillation of the rope, then the vertical slit will block it, and a horizontal slit will let it pass without any hindrance. Analogous to such selection of the polarization of rope waves through the rotation of a slit, the polarization of a beam of light too can also be selected by letting it pass through a light polarizer and rotating it appropriately, like you have rotated the slit from horizontal to vertical position to allow either the passage of the wave or block the passage of the wave. Similarly, the rotation of this polarizer will either let the wave pass through or block. The polarizer is the optical element that at a particular orientation allows light of a specific polarization to pass through while blocking the other polarization and imparting a 90-degree rotation to the polarizer will flip the polarization of the passing light, just as the rotation of the slit did. So this is how a polarizer, your sunglass polarizer, works. It actually blocks the S polarization, which is the majority of the reflected, the glare that comes from the shining surface. Let us explore how the property of the Brewster angle can be used to convert an unpolarized beam of light into a linearly polarized beam. We now know that when light shines on the interface between two optically transparent media, part of light is reflected back into the incident medium, while the rest is refracted into the second medium. Short, it was only known that the amount of reflection of light depends only on the angle of it. But the realization that the reflection of light depends also on the state of polarization was instrumental for the conceptualization of Brewster law. Now, in order to find the dependence of reflection of light from an interface such as that of an air glass, can be any interface. Let us consider air glass as a function of the angle of incidence for both P and S polarized light. We have to conduct an experiment, the schematic of which is shown here. For this experiment, we use a laser to have which can give both P polarized light as well as S polarized light. And this light shines on an interface between air and glass. And we place a detector appropriately so that it catches the reflected light. And the experiment basically involves measurement of the reflection as a function of the angle of incidence. So you change the angle of incidence, and accordingly you move this detector and catch the reflected light and measure the power, reflected power. Result of this experiment, first we are using P polarization. So the laser has been switched to P polarization. So it is giving P polarized. So the result of this experiment, that is reflection as a function of angle of incidence for P polarized light, is shown here. This is the reflection as a function of angle of incidence for P polarized light. It would be saying that at zero angle of incidence, the normal angle of incidence, the reflection is, this is about 4%. This is the value which you already know for air glass interface. The reflection at normal angle of incidence is 4%. However, as you increase the angle of incidence, the reflection for P polarization monotonically decreases until it reaches a value 0 at an angle which is actually 57 degrees. This angle is called the Brewster angle of incidence, theta b. So at Brewster angle of incidence, the P polarization shows 0 reflection, no reflection. And as the angle increases, this reflectivity then rapidly rises, becoming 100% at grazing angle of incidence, that is 90 degree angle. Understandably, at that angle of incidence, there cannot be any refraction. So everything is reflected. Now, second experiment, we tune the laser to S polarization and repeat the same experiment. That is, measure the reflected power as a function of the angle of incidence. And this is shown here. This is for S polarization. At normal angle of incidence, the reflection is again 4%, and that has to be because for a non-polarized light, that is randomly polarized light, both the polarization will be present of equal amount. So if Fresnel Fresnel reflection law says that a randomly polarized light with 4% reflection, that means both the polarization should also show 4%. So this also shows 4% reflection at 0 degree. Now as the angle of incidence increases, the reflection increases initially a little slowly, then rapidly, and eventually reaches understandably to 100% at grazing angle. But what is important is that S polarization always increases with angle of incidence, and P polarization first reduces, goes to 0, and then increases with angle of incidence. This angle of incidence is called, as we have seen, Brewster angle of incidence, for which P polarization cannot be reflected. And another important observation is that at Brewster angle of incidence, S polarization has a reflection which is 15%. So at Brewster angle, P polarization exhibits 0 reflection and S polarization exhibits 15% reflection. Another remarkable observation is that at Brewster angle of incidence, the angle between reflected, this is the reflected ray and this is the refracted ray. The angle between them is 90 degree. They make an angle of 90 degree between them. So let us now apply Snell's law and try to find out an analytical expression of this Brewster angle. Let us assume the refractive index of incident medium is mu1, refractive index of other medium is mu2. And angle of incidence is theta b, that is the Brewster angle of incidence. So the angle of reflection also would be theta b. This is specular reflection. The angle of incidence equal to angle of reflection. And angle of refraction is this. And because this angle is 90 degree, therefore this angle plus this angle should be 90 degree because this is a straight line. So this total angle is 180 degree. So if this is 90 degree, this plus this would be 90 degree. So if this is theta b, this angle is 90 degree minus theta b. So that to add them up, it becomes 90 degree. So basically then angle of incidence is theta b and angle of refraction is 90 degree minus theta b. So if we apply Snell's law for this refraction here, then mu1 into sin I. So I is theta b. So mu1 sin theta b equal to mu2 into sin r. So mu2 into sin r. R is 90 degree minus theta b. So this is mu2 cos theta b. So tan theta b is equal to mu2 by mu1. Now if you consider it has air and glass for which mu1 is 1, mu2 is 1.5. So you will see, if you plug in those values, then Brewster angle for air to glass interface will be 57 degree. This is precisely what also we have observed through experiment. Now let us see how this Brewster angle property can be used to convert unpolarized beam of light into a linearly polarized beam. So we first have a randomly polarized light, which we take a Brewster plate. When we say Brewster plate, that means we have taken a plate, the glass plate, and we shine light on it at Brewster angle, theta b. So we are using this plate as a Brewster plate because at this angle of incidence, P polarization cannot be reflected. It will be only refracted. So we are basically trying to find out how this Brewster angle property can be exploited to convert a unpolarized beam of light into a linearly polarized beam. So we have this unpolarized beam. Unpolarized beam of light is basically comprising of both polarization, S and P, and they're equally present. That's what we have seen. Unpolarized beam of light can be resolved into P and S polarization, and both would be equally present. So that is basically a randomly or unpolarized. Now S polarization is the one which is oscillating in a plane perpendicular to the plane of this paper. And P polarization is the one which is oscillating. So it is shown as this, and while S polarization is shown by this dot. That means it is going in and out of this paper. So this dot represents S. They are equally present. 50% is S polarization, 50% is P polarization. Now, if this unpolarized light shines on a Brewster plate, glass plate, where it is fallen at Brewster angle, theta b. So, P polarization cannot be reflected. So, only 15% of that, 15, if it were 100, this is 15% of this is reflected as S polarization. And entire P polarization is refracted. And then on the second interface, the same thing will happen. Whatever that 85% of the S polarization which is remaining, 15% of that will be reflected and rest will be refracted along with the entire P polarization, which of course would not be reflected. So S polarization is now reduced after suffering reflection loss these two interfaces, but the P polarization is intact. The entire P polarization is retained. Now we put another Brewster parallel to this. So this is again incident at theta, Brewster angle of incidence. So once again, 15% of the remaining S polarization will be reflected, and rest S polarization will be refracted along with the entire people. And then again, the same thing will repeat the second interface. So this way you see the refracted light, that is the transmitted light rather, will be gradually enriched in P polarization because it will be divided gradually with S polarization. And if you stack them up, number of such plates, then eventually you will get purely P polarized light, and S polarized light is gradually reflected away from the main beam. This is how you can actually, by taking advantage of Brewster angle of incidence, where P polarized light cannot be reflected, you take that advantage and convert unpolarized light into a plane polarized. So here you see you may need a number of such Brewster plates, but later let me mention here that in case of a laser, use of only a single Brewster plate would suffice to derive polarized light from a laser. How this is possible? This is because of stimulated emission. We will know how it happens when we study different laser systems. We will see how a single Brewster plate can make a laser emit polarized light. And if you just rotate the Brewster plate by 90 degrees, you can make the laser emit either P or S polarized light. The laser that was used for this experiment, I said that the laser should be capable of giving either S polarized light or P polarized light. That is how you generate polarized light from a laser. I think this is all about the different properties of light that I wanted you to know before we move into describing you different kind of lasers. Well, let me end here today.